Okay, so now we're on, yep, we're recording. Now we're on part 3, where we're talking about initiating therapy. So when we start therapy, we have to ask ourselves a couple of questions. First, is there a loading dose needed? Why would we need a loading dose? Well, there's two reasons. One is if it's a very urgent situation and we have a long half-life, and we want to get into the therapeutic range right away, pronto. So let's say your patient's having a seizure, or you need to get a drug to a certain level for surgery, etc. You're going to need to give a loading dose if the half-life is relatively long. Remember, it takes 5 half-lives to get to steady state. Therefore, if your half-life is 8 hours, it's going to take 40 hours to get to steady state. Is that acceptable or not clinically? That's what you have to decide. So is a loading dose needed? It's really about urgency and about weighing the half-life versus the time you have to get the drug into the therapeutic range. If you need to do a loading dose, what that's going to do, it doesn't get you to steady state faster. It just gets you to the concentrations you need right away. You still have to wait 5 half-lives to get to steady state, but you will be in the therapeutic range right away. You also have to think about dynamic considerations. So if it takes a while to, like, for example, if you're giving something that's going to block a receptor, right? It's going to take a while to block that receptor. So you have to think about how the pharmacodynamics as well, and the action of the drug. And because it may not make any sense to give a loading dose if you're going to have to wait for either maybe a receptor to decline or to block a receptor that might take a certain amount of time, and you can't really affect it by giving more of the drug more quickly. So you have to think about all these things. Loading doses are pretty straightforward. Remember, I mean, I like to think about when you're giving a loading dose, you don't have to worry about clearance, right? You're just giving the dose. So you've got, I think of the body as a beaker. Here's our little person. And there's a certain volume. Obviously, this isn't how people are made, but you've got a certain volume here. And if you want a certain concentration, so you have a target concentration that you want to achieve, you're going to have to figure out how much drug to give. That's going to be your loading dose, right? Because we know that concentration, could ask a lot of 8th graders this, concentration is amount over volume, isn't it? Amount per volume. So in this case, the concentration is our target concentration. The volume of distribution is how big is the volume of our patient, and the amount is going to be our dose of our drug, isn't it? So we can rearrange this to say that whatever our target concentration is, we're going to rearrange this. So we're going to say amount, or the dose, our loading dose, I'll just say loading dose, is equal to concentration, which is our target, times the volume of distribution of our patient, right? So we need to know what our target is, and we need to know what the volume of distribution is. Now, what volume of distribution do we use? Well, I gave that away because I said the VC. The VC is that initial, or you could call it V1, or people call it central volume, whatever you want to call it. It's where the drug distributes to immediately if you give it IV. So we're probably going to give it IV, and we're probably going to, want to give it to the initial volume. If we gave it to the eventual volume at steady state, we could easily overdose the patient. So we don't want to use that. We use our central volume of distribution times our target concentration, and then those volumes will cancel, and we'll have an amount, which is what we want for our loading dose. Okay, pretty straightforward, right? Okay. Oh, do that. Okay, oopsie, I need to clear. Well, can I do that here? Say goodbye, all you drawings. Okay, so now we have an example of a problem, don't we? We have JR, who's been admitted to the ER with acute asthma. He is started on a continuous infusion of an aminophylline. I will admit we don't often do this in therapy anymore, but it's an easy drug to talk about. So I apologize for not having a better actual world case here. But so we're going to give aminophylline. Aminophylline is a salt of theophylline. It's 80% theophylline, and theophylline is the active drug we're looking for here. So we have a target theophylline concentration of 12 milligrams per liter. That's what we're going to be targeting. So our target is 12 milligrams per liter of theophylline. Make sure we keep these straight now. So we're going to give a loading dose, and we're going to give it as a short-term infusion. Let's talk about it as before a short-term infusion. Let's pretend we're giving a bolus, because that's our easiest way to think about it, okay? So we don't need to worry about clearance if we're giving an IV bolus, right? An IV bolus is just going to be loading dose is equal to our target concentration times our volume of distribution. Now, we don't have a specific VC here. I'm going to have to assume that is the VC, but we don't know that for sure. We know that a population average is 2.7. So is volume 2.7 liters per hour. Wait, no, I'm sorry. 34 liters. That's given. Sorry, that makes no sense, right? Liters per hour is the clearance. So that's his clearance, and the volume is 34 liters. So sorry about that. I should have read the whole thing first. Okay, so 34 liters. And what's our target? 12 milligrams per liter times 34 liters. Those liters will cancel. And so 12 times 34 is going to be our loading dose. So our loading dose is 408 milligrams of theophylline. Because why? Because this 12 milligrams per liter is in terms of theophylline, right? So if we're going to give aminophylline, right, we're going to have, so this is our loading dose of theophylline. If we're going to give aminophylline is 80% theophylline. So we need to divide 4.08 by 0.8. The number is going to be bigger, right? So we're going to divide. So the loading dose of aminophylline is 510 milligrams. So the aminophylline loading dose would be, I'm going to say 500. You're not going to get 510. 500 milligrams of aminophylline if we're giving it IV bolus. All right. If we're giving a short infusion, that's going to change things, isn't it? I'm going to erase some here. If we're giving a short infusion, then we have to think about this being given over half hour. So this is at a half hour, we're giving some dose, right? And it's going to stop here. And this is what we want to be 12 milligrams per liter of theophylline. Okay. So we're shooting for this 12 milligrams per liter at a half hour. So now, since we're giving a constant infusion, if you recall, giving a constant infusion, we have to think about, remember, a constant infusion, if this is all concentration time, right? We're giving a constant infusion until we reach steady state. And you know that CSS steady state is just drug in or dose rate over, oh brother, what's my, go away. Over drug out, which is clearance, right? So we know that at steady state, our dose rate over clearance is going to be our CSS. But we're not going to get to steady state. We're stopping here at a half an hour. And if we stop at a half an hour, we know that we're going to only be at 1 minus e to the negative k t time of infusion, which is a half an hour, this will give us our fraction of steady state at this time t. Oh, right? So our Cmax is going to be equal to our dose rate over our clearance times 1 minus e to the negative k time of infusion. Now, this is not a steady state, right? Because we're just giving this one-time loading dose. So our Cmax, we know we want to be 12 milligrams per liter. Our dose rate is going to be our infusion rate, and our clearance we were given is 34, oh, I'm sorry, 2.7, do you think I'm going to get this straight? Liters per hour, right? Times 1 minus e to the negative k. Now, what's our negative k here? K is clearance over volume, right? So clearance is 2.7 liters per hour, and volume is 34 liters, isn't it? So that works out, because that works out to be point or per hour. And then we're going to multiply this times 0.5 hours. And that will give us, so we have to rearrange this because we're solving for our dose rate, aren't we? So you're going to do the algebra. So for this, in this paragraph, or in these parentheses, I got 0.0389. Okay, and that's a fraction. And let's see this. So I'm going to say 12 times 2.7 divided by 0.03. All right, so I got a dose rate of 832.9, and that's in milligrams per hour, right? But we're only giving it for half an hour, so we have to multiply. We're going to have to multiply in order to get our dose. Our dose is our dose rate times our time of infusion, right? So if our dose rate is 833 milligrams per hour, and our time of infusion is 0.5 hours, then our dose is going to be half of 833, right? Divided by 2. So I got 416 milligrams for the dose to be given over 1/2 hour. Now, we're still working in terms of theophylline here. So this would be theophylline. And then how are we going to convert it to aminophylline? Divide it by 0.8. So our dose of aminophylline will be 520 milligrams over 1/2 hour. Again, I'd probably change it to 500. Usually you're going to do it in 50 milligram increments or something reasonable. So the dose in both cases, for whether it's just an IV bolus or a short infusion of a half hour, would be 500 milligrams in this case. Okay? All right, what if no loading dose is needed? Oops. So we don't have urgency. So there's several different things you can do. You can start at the low end of a usual dosing range and work up to target the effect, or you can use some kind of population approach where you look at what has happened in the past and you try to guess the best dosing regimen for your patient. So when we say something like 5 milligrams per kilogram, that's based on population averages. So does your patient match that? Maybe, maybe not. So you're basically using what we've already learned to try to get as close as you possibly can and then make adjustments. So the population approach will start the dose with some individual data, like the weight of a patient, like we said, like 5 milligrams per kilogram. Make sure you consider concurrent diseases. So you need to look and see how is this patient's renal function or hepatic function, or is there any reason to think that they're going to have binding changes, et cetera. So you have to think about disease states and how that might affect the patient. You also want to think about drug interactions, all the drugs that the patients may on. So inducers and inhibitors of the CYP system or P-glycoprotein, or drugs that will compete for tubular secretion sites or compete for enzyme sites, or things that will alter plasma protein binding, as we mentioned, things that will alter dynamics. Genomics is something that we're learning more and more about, and we can use to start doses appropriately, fast or slow metabolizers. All right, and lastly here, some drugs are more forgiving than others if you make an error, right? So if you have to think about pharmacodynamics, if there's a counterclockwise hysteresis, that's going to give you more time to make up for if the patient has missed a dose or not. And if we're dosing less than every half-life, then you also have a chance you might miss a dose and still be okay. So you have to think about all these things when patients miss doses. All right, next we're going to talk about adjustment and maintenance dose, but I'm going to stop this one for now. See you soon.